Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be talking about polyprotic systems and trying to figure out exactly what protonation state they might exist in. So this may seem a little esoteric, but it ends up controlling a lot of our day-to-day lives. So polyprotic systems essentially end up being present all over the place. And so this can include things like phosphoric acid and sulfuric acid, but it also ends up encompassing most of life. So one of the more important polyprotic acids is amino acids. So these are the building blocks of proteins. So there are 20 amino acids, and when you combine these together, you can end up making big, long chains that form the proteins that do everything involved in life. The basic structure of an amino acid includes three major groups. So the first of which is this carboxylic acid, the second of which is this amine, and the third of which is an R group. So the R group is essentially a name for some random organic chemistry group. So in this case, these R groups are one of 20 different organic chemistry groups. So these can include anything ranging from hydrogen to acids to bases to a lot of different species that you'll learn more about in organic chemistry and biochemistry. And the exact choice of R group can control a lot of different properties. However, it is worth noting that every single amino acid will contain the same two basic functional groups. They'll contain this carboxylic acid and this amine base. And it is worth noting that this means that every single amino acid in your body, which exists both as proteins and free floating, will demonstrate acid-base behavior. And so most of these carboxylic acids are going to be quite acidic, with pKa's somewhere between about 2 and 3. In contrast, the amine bases have pKa's somewhere between about 9 and 10. So they aren't quite so acidic, but it's worth noting that what I currently have shown is actually the conjugate base of the amine form, as the amine can actually gain a proton with a pKb of about 4 to 5, which is actually a fairly good base. And it is worth noting that if we know these two pKa's, we can go ahead and, for a given pH, try and determine whether the species is likely to be protonated or deprotonated for each of these individual groups. And this can dominate what the amino acid can do in your body. So let's go ahead and start with the simplest of amino acids, which is glycine, where our R group is going to be hydrogen. So I didn't just drop a group here. This will actually be a CH2 group, and this is going to be a straight carbon. So this is actually relatively simple as far as amino acids go. However, it is worth noting that it still can possess two different acid-base reactions. The first of which is going to be that carboxylic acid, which can lose a proton with a pKa of 2.35. So again, fairly acidic. And for the amine group, it has a pKa of about 10, meaning that it is likely to be protonated. And one of the very useful things we can do with these pKa's is can compare them to the pH of the system to determine whether each group will be protonated or deprotonated. So if the pH is less than the pKa, it means the system has a whole bunch of protons, and according to Le Chatelier, will tend to favor the reactants. In this case, it means that they're likely to be protonated. So this would be an NH3, and this would be a protonated carboxylic acid. If, however, the pH is greater than the pKa, it means that we have rather fewer protons. The system is fairly basic, and this means that Le Chatelier will send the system raging forward to generate more protons. So the carboxylic acid will actually be a carboxylate, and the amine group will be, well, the deprotonated amine. So if we go ahead and compare a neutral pH of 7 to these two different pKa's, you'll find that the pH is greater than pKa1, so the carboxylate will be deprotonated. But it's also less than pKa2, so that means the amine will likely be protonated. So this means that under neutral pHs, the natural protonation state for glycine and most amino acids is actually a little bit weird to our eye. And it is very rarely drawn as this way, but if you're actually in the body, it's important to know that amine group is actually going to be positively charged and protonated, and that carboxylic acid will be deprotonated and negatively charged. And so this type of molecule has a very special name. It is called a zwitterion, as it possesses both a positive and a negative charge on the molecule, but the overall molecule itself is neutral, which means that you can actually throw glycine without it being present as a salt straight into water without any counter ions. But as soon as it reaches water, the proton will move from one location to the other to generate this species, which I'll represent as HA because it is singly protonated. And if we end up decreasing the pH to below 2.35, what we're going to find is that carboxylic acid will end up becoming protonated, because this way I have a pH below both pKa's, and ta-da, we end up generating H2A+. So in this fully protonated state, we have a single positive charge. Under high pH conditions, we tend to see the system will become fully deprotonated, as we have no more protons to give, and this will occur for any pH above about 10. However, it is worth noting that you can still be fairly close to either of these pKa's and have the system both protonated and deprotonated, as remember the pKa's mean that both acid and conjugate base are going to be present at once. So if we want to find the exact ratios of each of these species, we'll have to use Henderson-Hasselbalch, which again says that the closer the pH is to the pKa, the closer that ratio is going to be 1:1. When the pH is exactly equal to pKa, I'll have a 50% mixture of acid and base. For whether if we're at a pH of 2.35, it means that I've got both the doubly and singly protonated species present. If the pH is closer to 10, it means I've got both the singly and doubly deprotonated species present. And when I'm far away from any of these pHs, so if I'm at very high pHs, I've got just the deprotonated state. When I'm at very low pHs, below 1, I'd have the fully protonated state. However, under neutral pHs, I'd expect to have this amphiprotic species, which can both gain and lose a proton. Now, if I throw essentially my base form in, I can imagine getting its pH just by essentially using a weak base calculation, as I only have to care about the highest pKa. Similarly, if I throw in my acid form, I only have to worry about the lowest pKa. But if I throw in this amphiprotic species, it turns out that the pH would essentially be at the midpoint of the two, because it doesn't want to gain or lose a proton. So it's going to try and stay as far away from these two different pKa's as possible. So you can find the pH of an amphiprotic species simply by taking the average of the two pKa's. So in this case, it turns out that glycine and a lot of the amino acids will have a pH for the amphiprotic species of around 6. Now, one of the other useful things to do is to try and figure out the exact relative abundance of each of these individual species compared to how much total glycine is present in the system. And you can get this using what's called the alpha value, which really is just a fractional abundance. So if I care about the alpha value for my amphiprotic glycine, so this would be actual glycine, this will be the number of moles of the monoprotonated glycine versus the total moles of the fully mono and fully deprotonated states. So if you can imagine, when we're at a neutral pH, I expect it to mostly be HA. At low pHs, mostly fully protonated, and at high pHs, mostly fully deprotonated. And you can end up generating what are called alpha plots. And this is exactly what you tend to see. At pHs, essentially less than 1 pH unit below the pKa2, you will stop seeing the fully deprotonated species, as it just isn't really there. And if you look at the acid species, it will dominate below it will almost exclusively be present less than 1 pH unit below the first pKa. At the first pKa, it will be an equal abundance with the monoprotonated species. However, once you get past the pH of about 3.35, so essentially more than 1 full unit past this first pKa, it's pretty much no longer present, and only the monoprotonated species will be exclusively present. Then again, you'll see a very similar trade-off as you go to high pHs. And so if you go ahead and try and look at a polyprotic species and try and figure out what sort of activity is happening, one of the first things you need to do is construct an alpha plot to figure out which one of these molecules is most likely to be present. And it's worth noting that this doesn't just apply to amino acids. This can be applied for any polyprotic molecule. So another very common polyprotic molecule that is pretty much in any aqueous system is going to be carbonic acid, because it turns out that carbonic acid can produce bicarbonate in water, which can then further deprotonate to form carbonate. And all three of these species can be present depending on the pH. So if I want to know what sort of reactivity is happening in water, I need to again construct an alpha plot to figure out who dominates under any given pH condition. And this is especially worth noting because if I add CO2 to water, like global warming does and like most soda streams do, it ends up entering as carbonic acid. So this is a good way to make sure that you have just this low pH system with lots of carbonic acid. However, it turns out that many rocks are composed of carbonates. So this goes anywhere from limestone to just the soap scum on your sink. These are mostly carbonates. And so these tend to only really dominate at high pHs. Under neutral pHs, it turns out that most water will be relatively high in bicarbonate. So this is what we think of as baking soda. So depending on your pH conditions, you could have something that tastes fairly sour, something that's fairly basic and leaves residue on all of your appliances, or baking soda. And it turns out that there will always be some level of one of these three species present in almost any aqueous system. And we can again track this as an alpha plot. At pHs below about 4.4, we're mostly carbonic acid. In between about 6.4 and 9.4, it's mostly going to be bicarbonate. And under high pHs, it's mostly carbonates. It's worth noting that most limestone will end up forming under high pH systems. And it is also worth noting that if you go to a lake that's surrounded by lots of limestone, it tends to be fairly high in pH. However, it's also very worth noting that most life exists at a pH between about 6.4 and about 9.4. And it turns out there's a very deliberate reason for that, because this is the region under which bicarbonate is present. So it turns out bicarbonate acts as a buffer for most aqueous systems. If you add too much base, congratulations. This first buffer region prevents you from moving. The second buffer region prevents the pH from going too high. If you add too much acid, this first buffer region prevents the pH from going too low. By having bicarbonate in any aqueous systems, it makes sure that the pH stays in between these two pKa's. So it turns out that making use of polyprotic systems and their fractional composition is really important, because it prevents our systems from becoming too high in pH, where we become exclusively carbonate, or too low, where we end up going exclusively to carbonic acid. So next time, we're going to be going ahead and looking at how we can move through all these various protonation states as we start doing titrations of polyprotic acids. Until then, take care.